giving me opportunity to like share my research work as well as to share some of the topics which where I'm interested in and where the entire global world is looking at the technologies. So let me share the slides. Is this slide shared?
Yes, sir. It is coming. Yes, sir. Can you enlarge the screen, sir?
Enlarge. If I enlarge, is it moving?
Yes, sir. Visible, sir. If you, I think it is in Word document.
No. No. I mean to say, is it slides are moving or not?
Moving, sir. Moving, sir.
Moving.
Yes.
Slides are moving now.
Yes, sir.
Okay, then. So let me start the session. In between, you can interrupt me if you have any queries. I'm ready to answer. So the topic of my talk today is novel materials for sustainable energy conversion and storage. This is the outline of my presentation. I've been discussing what is the need in present day, the sustainable energy conversion and storage, what are the issues and challenges, and I discuss a few part of overall materials existing, and then I shortly glimpsely cover some photoelectrochemical cells which we use for production of clean fuels like hydrogen and oxygen, and then some part of my talk consisting of two-dimensional materials for battery and supercapacitor applications. Well, I start with the slide where in the entire global world is looking at the
A small interruption, sir.
yeah.
Sir, the screen is very small, sir. The participants are saying in the chat box that it is not visible. Please make it full screen.
Sir,
I've
F5
been
cotton,
kept
sir.
in the large mode only. Why I don't know.
Sir, F5 cotton, sir.
F5 లోనే ఉంది. F5 లోనే ఉంది. ఇప్పుడు మూవ్ చేస్తున్నాను. మూవ్ అయిందా స్లైడ్స్?
Move, sir.
Slides move అవుతున్నాయా?
No, sir.
No, that is what the problem. I understood because this is what earlier also I faced. Okay, I do one thing. Maybe these slides are moving now. The screen size is less, but I can like we can fit it at least. Okay. Is it moving now?
Yes, sir. It is moving, sir.
Yeah, fine. So because I have been facing this, I don't know, maybe the some settings in my system which not allowing me to present the entire screen. It's okay, so that's not a big issue, and you can interrupt me at any point of time if you have any queries regarding what I'm talking in the presentation. So this is what the outline majorly focusing on the 2D materials. What anything?
Siddharthi, can you mute?
Yeah, the first slide of my presentation talks the humanity's the top 10 problems. See, if you look at this slide, wherein maybe there are some problems which I have put up here: the water, food, or education, population. But amongst these things, the two most important problems which entire global world is facing is energy and environment. Like as for the one of the journal publication says, the 21st century, the energy is the single most important scientific and technological challenge that everyone has to face in the entire global world. No, that's what I have chosen this topic of novel materials for sustainable energy conversion and storage. So let me introduce the contents. So the main intensity of this presentation is like talk about the materials. So why we talk about the materials is the discovery, development, and deployment of materials has always been the significant factors in development of human civilization. Well, regardless of their novelty, but the fundamental materials all useful for the technology and economic activities, and entirely depending on the materials and materials technology play a prominent role. So what I want to discuss, maybe the materials which may come from the polymers or glasses or liquid crystals, but the revolutionary changes in material synthesis and fabrication gives direction towards development of new technologies. However, there are two important points which are I focus in this talk: the scarcity in technological innovations, because that will lead to sustainable development of materials and subsequently conversion and storage. Well, what exactly the topic of my presentation is: the novel materials for sustainable energy conversion storage. What it aims is the state of art of novel materials and the engineering the device architectures for different energy conversion applications. Maybe it consists of electrochemical cells or photoelectrochemical cells or batteries or supercapacitors or fuel cells. Now, let me talk about the first definition of a novel material. What we mean by novel material is the existing materials can be called as a novel. So, different authors have been given different definitions. And let's see the first definition. The first definition says any material which is unused or rarely used on an industrial scale, we can call it a novel material. For example, rhodium or yttrium or some compounds derived from them can be called as a novel materials. Or sometimes which may not have the characteristics which has been developed even though they exist. That's the second definition. For example, silver and gold, two important metals which are already there in the prehistory, but nano silver and nano gold, that means the properties at the nano level different from the bulk structures, they can also be called as a novel materials. Or sometimes their applications are extending and are improving the efficiencies, can also be called as a novel materials. For example, if you look at diesel engine, the improvement in the efficiency of diesel engines can be much improved if you add material called cerium oxide. So that also comes under the novel material classification. Sometimes the last definition gives new pathways or destinations, which we call as some microscopic plastic particles arising from mechanical action in marine ecosystems, can be classified under the novel materials. Okay, whatever it may be the definition of novel material, but we discussing the important four sectors here in my talk. Well, before discussing why we need to study the sustainable energy conversion storage, what is the need? Because that is was the first headline in my outline. Like for example, if you see this slide, the maybe the primary energy which we are deriving or extracting from different sources, let us say it has some 100 joules, but when it is transported to the household, let's say maybe some transmission lines, electrical transmission lines, we so it will reach up to maybe 50 joules only. And perhaps from that 50 joules, if you ignite a light, for example, I have showed you here the light, which may takes into account of some 2 to 8 joules. That means what? Rest of the energy is being lost either in the form of heat or in other forms. So major fraction of energy is lost during the conversion and the transport. So for example, even if you look at this, the other part, maybe I can skip because I have kept it in the what we call the animation mode, whatever it may be. So here the main important is we need to focus on the development of sustainable energy conversion and storage technologies. So although I have showed you some four important themes of my presentation, but other areas wherein this sustainable energy and conversion storages are like maybe the carbon dioxide. We are seeing the rises in carbon dioxide leads to global warming, and we need to focus on less carbon footprints. So maybe the if you could convert this carbon dioxide into some useful fuels, and that from fuels we can use or we can extract some other energies. Okay, so that is another area, or some area called thermal storage or photocatalysis. So these are the different other sectors wherein we need sustainable energy conversion and storage devices. But before going to the actual content, let us discuss some primary energy sources where we have the energy and what we are looking at in today. Like see this slide wherein let us say but our population maybe in around 2019 the statistics says the overall population is around 7.7 billion. But if you could look at the same population, maybe the year of 2050, if you could extrapolate, maybe it is 12 billion. So the population is increasing like an exponential, but where you're getting the demand energies for this population, majorly oil sector. If you could look at this bar plot, maybe 36.4% of oil is required to forecast the energy at the global. Apart from the oil, some natural gas or coal or other forms, maybe of less percentage. But if you look at the demands, maybe in terms of barrels of oil equivalent, you see the sectors of transport or a power or industry, they've been increasing like anything. Maybe in 1970s, we may need maybe around 40 barrels of oil equivalent. But if you look at 2030, if you forecast, it has been rising to around 130 barrels of oil equivalent. Is from the other sources. Or where we can look at the demands or supply, see the transportation sector or buildings or industry or power. So different forms of energies have been supplying different forms to the different sectors to meet the demands. So overall, that may be the calculation, but what is the intensity of these slides is the depletion of the existing fossil fuel sources. If you look at this graph, the coal or natural gas are diminishing from time to time, whereas we need to look at some alternative renewable energy sources, which at present day the main focus is. So this is what the left side graph, which shows the tons of million tons of oil equivalent compared to the present day scenario with other energies like coal, oil, gas, or nuclear. So this is what the million tons of oil equivalent BAU, business as per analysis, one of the consultancies where the other energy sources, the rates which has been shown. So what are maybe the sectors, we need to look at the conversion of these energies into useful forms and what are the what we call the issues in conversion. If you look at the issues, maybe if I, for example, I showed here the image, the fossil fuels which we convert into some energies, definitely it leads to carbon dioxide which we need to capture, and then after capturing it needs to be converted. Maybe we use some energy for conversion that may be from renewable energy sources, and after all, after doing all these things, what is ultimately we've been left with is, are we run out of the materials, or do we have enough materials in conversion or storaging of all these energies? This is what the central theme of my presentation, which we will go. Of course, along with the issues, there are some certain challenges also which we need to like overcome. For example, in earlier days, I already discussed the diesel engines. The improvement of efficiency may be the first of all the basic challenges in earlier days, but now it has been overcome by addition of some fuel materials like cerium oxide. Maybe sometimes the jet engines can burn at much higher temperatures when rhenium is added in alloys in construction. Similarly, uh, uh, what we call the innovation of lithium compounds, which will improve in the cathodes of lithium ion batteries. Maybe the problems of hydrogen. Earlier, there is a biggest challenge in storage of hydrogen. How do we call like change the storage the hydrogen? Maybe in the form of hydrates. Fine. So along with metals like platinum, palladium, nickel, and magnesium. So sometimes what we call the implement of or innovation of conducting polymers, oxides, or silicon nanorods or carbon tubes. So earlier these may be the challenges, but now the innovation of materials or the technological developments made to overcome the challenges which were there in earlier days. No, for the basic background of all these challenges or the issues to overcome is the materials. Now, how do we understand the materials first? Because maybe if you take a copper wire, or if you take a slab, or if you take a tire, what are there inside all these things? Maybe if you look at a copper wire, it's a metal. So metals will conduct electricity because some electrons free themselves from their orbits and can flow through the material. Maybe the concrete. which can interlocks the particles of sand and gravel. So that's a very important material which can what we call the interlinking agent. Maybe if I take a tire, what are the polymer chains which are very flexible, rigidly locking the chains together and increases the durability of the material. Maybe if I look at a periodic table, whatever the four themes which I have chosen for this presentation, like batteries or photovoltaic cells or fuel cells, or maybe the photoelectrochemical cells, look at the periodic table of elements wherein I have been given the four different markings. Maybe the green color of the materials which we use for the photovoltaic or solar cells. Like what are the elements here? Either silicon, phosphorus, gallium, germanium, arsenium, silicon, selenium, indium, tin, or tellurium. Maybe for hydrogen storage, we go for titanium, starting with the material titanium, vanadium, manganese, iron, cobalt, nickel, series. Or for the fuel cells, basically we go for the platinum, which is a very important metal which we use in the fuel cells, or lanthanum, zirconium. Or in the batteries, the fundamental periodic element which we use is the lithium, or cadmium, or sodium, even because the sodium ion batteries are there, cadmium batteries are there, lead batteries are. So, in a periodic table, though different elements which we choose to synthesize the materials, but at the end of the day, we will look at sustainable energy. That means what we give with the less content of energy to extract and bring it to the nature with some cubic volume. So we'll go with some concept called dematerialization. Even if you look at like utilization of less to give same service. For example, take a mobile. If you take a mobile, what is the material content in weight percentage? If you look at this cartoon, maybe around 27% of iron is there in your mobile and 27% thermoplastics. So maybe 15% battery and rest of the contents maybe magnesium or copper or some plastic or rubber materials. But for example, if your mobile has been have some problem or it has been old or outdated, now in order to like go for a new mobile, or can we change the existing mobile with certain modifications? So what we look at a concept called dematerialization, wherein we will like repair, resell, or reuse, or components we can reuse, or certain redesign, so that same service can be brought in utilizing the lesser materials. So that is what the concept of what we call the innovative technologies, wherein we focus on less carbon prints or lightweight materials, which we give the more compact, maybe technologies like nanotechnology. For example, look at a slide of Eiffel Tower. And for example, how much amount of steel is used in constructing this Eiffel Tower? If we could redesign, with some designer steel, or steel with made up of some nano composites, which will be of very lightweight, then we've been succeeded in this era of modern world, because our the intention is go with less materials but get the same service. Even this is what the demands year to year. That's most important materials called cement, steel, paper, aluminum, or etc. Though they what we call though they exist in the world or in the history, but we need to look at the most prominent utilization. So what we call some graphs as big graphs. Maybe you can see the as big plots. These are the plots generated by plots the two components for so many materials on the two angles, wherein we can choose the component which we require at the desired characteristic level or the desired property. For example, this is the property of Young's modulus versus embodied energy. What is embodied energy? Is the whatever the energy that is required to get it from the nature. Now you look at the different sectors of materials, maybe polymers or metals. So what is their location, and what is the embodied energy per cubic meter. Can we replace that material with whatever my Young's modulus which I am desired? So like that, he has plotted different plots. Maybe I can show you some of the plots. Maybe this is the strength part, a plot where strength versus embodied energy has been plotted, where the desired strength can be chosen at a required embodied energy. Like for example, I want to give only less amount of energy, wherein the location of my material I can choose. For example, let's say my embodied energy is maybe 10 power 5 only. Now if I look at the scale of 10 power 5, what are the existing materials? If I could choose the material at the desired strength, I will be happy, rather than going with an extreme case of embodied energy or extreme case of strength without losing the harmful characteristics or without losing the cost factors. Maybe the other plots, like maybe in terms of price or in terms of carbon footprints, even whatever may be the characteristics, because he has plotted several characteristics on the two axes, wherein we can choose the required material at whatever our desired levels. Now, maybe he has generated some tables also. This is the embodied energy for different materials he has generated. Now, what is the take-home message from these tables or the plots is what kind of energy is embodied in that material and what kind of efficiency we've been looking at. So we can easily pick out the material at our desired levels. Now, the next slide is the betting on the planet. Maybe if you maybe it's like a surprise. If you go around in 1980s, there is an article in Science where there are two important professors in science. One I have showed you the slide here, Professor Julian Simon, and who is at the University of Maryland, and another scientist, Paul Ehrlich, who is professor of Stanford University. There's a bet in these two guys, wherein what Simon has like open challenge to Paul Ehrlich is, if scarcity rises due to population growth, then the prices of natural resources like grain, oil, timber, metals, etc., should rise at any future date. Now, this challenge has been taken by Paul Ehrlich very openly, and he bet for $1,000 by taking the five important materials. Now, I hope you understood the challenge. The challenge is Simon has given an open challenge that there are whatever the resources available are not finite. We can have infinite sources of energies or infinite sources of materials where they cannot lose even in time. But what Paul Ehrlich accepted whatever the Simon said, and I will prove it's wrong. And he has betted for $1,000. This is the famous bet in the year 1980s. Now, so Paul, what he has taken is he took some five important materials like chrome, copper, nickel, tin, and tungsten, and then like each material costs around some $200 at that time, and totally some $1,000. And what is the bet is, if these cost of these materials maybe for 10 years, let us say from 1980 to 1990, if the cost is less than $1,000, then definitely Simon has lost, and the difference of amount has to be paid by the other party like Paul. But if you look at, like, maybe you can guess who has win in this bet. Is very unfortunate that Simon has what we call Simon has got the bet and Paul has loosened the bet. Maybe the bet was not conclusive results, because maybe in the span of 1980 to 1990, maybe the whatever the materials he took, maybe chrome or copper, they in fact they used to downfall in the 1990s, but usually we expect to be increased, because always there will be scarcity of the materials. But what this bet has given to the entire world, a statement of two important things like scarcity and technological innovation. Like if you does not, if there is no scarcity, there is no innovation in the entire world. So scarcity is an evident thing, as well as innovation and improvements in the technology is also very important. So based on these, the bet gives to the entire world that we need to focus on all the time the innovations and improvements in the new technologies. So therein it lies a major responsibility for material scientists to create new materials or novel materials. So with this brief introduction, I've been moving to some of the concepts, and then quickly I will wrap it up. And where I want to focus more, I will focus or give more time. So maybe the next slide, like the conversions majorly from solar to chemical, or solar to electrical, or vice versa, or from electrical to chemical, which major theme of my presentation talk: batteries or supercapacitors or electrochemical cells or photoelectrochemical cells. Because basically we have been involved utilizing the solar energy, the photons of the sunlight, we can call as photoelectrochemical cells, wherein we can produce hydrogen and oxygen, very clean fuels. So first of all, I'll handle the electrocatalysis part. Then I will move to the photocatalysis part. Briefly, I will talk about the important applications of electrocatalysis. Then I will quickly move to the other parts of my talk. Maybe this slide you might know. Maybe if I could look back, the important reaction. This is a photosynthesis reaction. Six molecules of carbon dioxide and six molecules of water gives rise glucose and oxygen, which we desire and require. So if I relocate this reaction, and if I could break the chemistry part, if I look at very carefully in detail, there are a lot of ionic reactions and electrochemical reactions wherein the electrochemistry plays an important role. This is a Kevin-Benson cycle, which has been studied way back very, very confidently and clearly, and explain the role of electrochemical species and ions. Maybe the importance of ions or the electrons is also very important in the case of adenosine triphosphate to adenosine diphosphate. Maybe the one molecule of water reacts with adenosine triphosphate to break it into form or remove one phosphorus molecule to form adenosine diphosphate. So again, if you could break that one, and if you could understand, again there is an important involvement of electrons and ions. So more or less, people have been studied the electrodialysis, where different membranes like cation transfer or anion transfer, where ions can be moved. Fine. So along with the ions, there is an electron transfer. So these are all very, very good examples of importance of electrochemistry, where the electrocatalysis plays an important role in all parts of the sector. Maybe for example, the electronic tongues. See, for example, maybe gluten is a very important protein which we found usually in barley, rice, or wheat. But we don't know how much content of this protein is important for the body, human body, without contamination. So how do we find out the unknown gluten content in the foodstuffs? So basically, the utilization of these electronic tongues, e-tongues. So people have been designed these e-tongues, and again the basic chemistry involved is this electrochemistry, where we look at what we call the content of ions or species, and then convert it into the electronic messages. Maybe the glucose sensors, the earlier days, like maybe the people who are suffering with diabetic, they have to spend maybe half a day time in taking their glucose levels, sugar levels, before fasting or after fasting. But now it is not an era come where we no need to go to an hospital. Just spend maybe less than a minute to get your glucose levels. So the sensor has been developed, which is costing less than 5,000 rupees in the market, which has been designed only the involvement or innovations in the electrochemical area. So this is the sensor. The main mechanism is glucose glucose in terms of glucose oxidase convert into gluconic acid and hydrogen peroxide. And this is the mechanism, and perhaps other utilities like breath sensors have been already also developed based on the electrochemical technologies. And then maybe the signage detection, very important one in the gold gold, what we call gold synthesis. So the reason is because the gold is available at very, very less contents when we extract, and we need cyanide. No utilization of cyanide, we can extract the gold, but how to destruct this cyanide? So there again, the electrochemistry plays important role, because cyanide presence making the gold to be before it may be inert, but it is contaminated in presence of cyanide. So again, the role of electrochemical chemistry is involved in this cyanide destruction. And the important part of electrocatalysis, electrolysis of water, where two half reactions will take place to form hydrogen and oxygen. We can call as half reaction and then reduction half reaction. So upon application of potential across the two terminals, we will get hydrogen and oxygen, which we collect and which are pure in the sense. So this is all electrolysis of water. Maybe the other parts like entire battery technologies is electrochemical technology only. Maybe it may be the percolation of lithium ions from anode to cathode, or sodium ion batteries, or alkaline batteries, or lead acid batteries, or silver button batteries, which we have in our daily day-to-day watches. So all in all, they use the technology of electrochemical knowledge and science in developing all these things. Perhaps lead acid batteries, of course, nickel metal hydride batteries, and maybe the inverters, or an important medical field we call as a pacemaker, which is a small device that helps your heart beat more regularly. Maybe it can control the heartbeats, but the battery inside the pacemaker, again, the reactions are electrochemical reactions only. Maybe the lithium at the anodic part, and then silver vanadate at the cathodic part. And ECG, mainly if you look at the ECG part, where electrocardiogram, which can diagnose the heart abnormalities. Perhaps all whatever the medical uh, uh, developments in today's scenario primarily utilizes the multidisciplinary sciences and technologies, maybe ECG or electron encephalogram, EEG, which detects the brain disturbance, okay, or the what we call the any blood clot in your brain, which can senses and detects. Even the electromyography, what we call the nerve function, losing of nerve function, it can detect with simple electrodes. If you could fabricate an electrode which can senses and gives the direction of detection very easily. We can, electrotherapy is there, and then very large application of electrochemical in sciences, maybe chloroalkyl industries or aluminum productions, maybe the paint industries, textile, leather, and then maybe what we call water treatment and sensors. I have showed you some glucose sensor, breath analyzers, and then very rapid penicillin electrodes, uric acid electrodes. So all what we, maybe the last part which I can discuss is the fuel cell. The chemical energy is converted into electrical energy by utilization of hydrogen and oxygen at the two ends. So even this, what we call the present day fuel cell cars, which has been running in maybe the developed countries, I can say. Perhaps I can say in India also there are some cars, electric cars have been started in Delhi, and then some part in the Bangalore. And the technology is like there are different categories of these fuel cells depending on the operating temperatures or the electrolyte mediums. We can call as proton exchange membranes, or direct methanol fuel cells, or alkaline fuel cells, or some phosphoric acid, etc. So perhaps whatever may be the classification, but all in all, it has been utilizes the electrical energy in one way or around. Maybe here the chemical energy is converted into electrical energy. So this is electrocatalysis. So whatever may be the forms here, let me go through the fundamental concept of photoelectrochemical cells, because that's what my area of research, wherein we use photon light in converting water molecule into hydrogen and oxygen. So let me go back to the energy demands and the intensity of my work. Maybe we know that energy crisis. For example, the total energy needed at the global level maybe around 0.63 terawatts, but plenty of energy is available from the sun, maybe 1,20,000 terawatts. But this is a big problem is sun's light in reaching the earth. There's a dilute form, and we need development of catalysts which can utilize in converting these solar energy into useful forms among the renewable energy sources. So perhaps there are so many forms, agencies, maybe in India, across the maybe in foreign countries or across the globe, which can give some subsidies in getting the solar energy, or we can call as solar cells. So what basically photoelectrochemical water splitting says, it utilizes sunlight photo energy to break the water molecule to form hydrogen and oxygen. So it combines light harvesting system and then water splitting system into a single device. So I can show you the slide wherein there will be two electrodes, and on the one electrode we will impinge the solar light, and this solar light, what is called the photon absorption, creates electron and holes because we use some semiconductor materials, and that hole will be reacting with water to produce what we call hydroxyl radicals, which we call as an oxidation, and then same at the other end of the electrode we can form hydrogen. So overall water splitting reaction is two molecules of water reacting with four number of photons to give hydrogen and oxygen. So here the most important part, maybe we will look at a photoresponsive semiconductors, but there are so many factors in converting this photon energy into useful forms of hydrogen and oxygen. So if you look at the microscopic level, I can show you the slide where there are three important factors which drives the entire photoelectrochemical water splitting. The first part is the photon absorption. So whenever we impinge light onto any semiconductor material, the whatever the energy that is coming from the sun or photon energy should be greater than at least or equal to the band gap energy. Then only it can create the electron hole pairs so that the electron can move from the valence band to the conduction band. Now, so after getting the electrons and holes, because there is a quenching, or we can say very less time of relaxation for the charge carriers which has been split in the photon absorption step, we need to separate it. So that's what the second step, charge carrier separation and then transport. So even if you separate, there should be some species needed to get react or get extract the electrons and holes, which we call as the electrochemical reactions on the surface, which wherein oxidation or reduction reactions, for example, reduction reaction will be facilitated with electron and oxidation reaction facilitated with the hole. So overall, I can say the photoelectrochemical efficiency, which is a function of three important factors, that is absorption, charge carrier separation, and then what we call as surface electrochemistry. So if I look at materials perspective, whatever studied in the literature and what we are intentionally needed to study, we look at it, the whatever the materials already have been studied, because the any photon absorption, because we know in the solar spectrum almost only maybe less than 5% of UV light is there, and the other parts like maybe 40% is the visible light. So if we could target the spectrum of visible light, and I have given here the target where we are looking at quantum efficiency maybe 10 to 100, and the visible light in the span of from 400 to 600, I can convert major fraction of the solar energy into in producing clean fuels like hydrogen and oxygen. Now, what are the barriers in conversion? If I look at, this is the barriers when I want to move to get high efficiency metrics in PEC water splitting, what is the target roadmap? Because there are a lot of technical barriers, maybe the materials durability or efficiency or device configurations. For example, maybe I have to look at materials with low band gaps and feasible band energetics at the same time, abundantly available, and they should be cheaper in cost, and they should be stable if I operate for more or duration the lifespan, and so that I can reach to maybe around STH efficiency, that is solar to hydrogen conversion efficiency, maybe around 15%, because we will not reach it to that because of the long limiting barriers in the conversion of this solar energy into useful forms of hydrogen and oxygen. So what are the approaches in meeting these requirements? Is either you should develop completely new materials or tune the existing materials to the desired property levels. So, so what we can do? Can we develop a new entirely material, or look at the material, existing material, take that one and tune the properties so that we can reach to the whatever the target map which has given by so many organizations. Maybe I can show you the whatever the barriers in all the three uh, functionaries. I told you the photon absorption, charge carrier separation, and surface electrochemistry. Maybe the first part, if I take the band gap photon absorption, band gap energy engineering is one of the prominent factor. Like, for example, how do we improve or how do we tune the band gap? Either by doping with non-metal elements like nitrogen, sulfur, or phosphorus, etc., or we can go by sensitization using some dyes or use some plasmonic metals like gold, silver, etc., wherein we are creating some mid-gap energy states and oxygen vacancies, wherein we will shift the absorption to the visible fractions. And whatever the improvisations in the charge carrier separation, maybe you can improve the crystal structures by forming some heterojunctions or composites, so that the particle size can be controlled. At the same time, the crystalline nature or the crystal structures can be more often improved. And the other part of the surface electrochemistry is how do we improve the, because after even separating the charge carriers, we need what we call the fast taking extracting species for the reactions. Maybe it's an oxygen evolution reaction or hydrogen evolution reaction. Maybe if you increase the surface areas or active sites or some co-catalyst like platinum, gold, which can quickly take the electrons or the holes, and they can like close the entire the photoelectrochemical water splitting reaction. So with this thing, I have started with my first work in my PhD with the titanium dioxide material. So at that time, I have understood there are a lot of literature on the titanium dioxide, and what I can do or what I can make the material to be novel so that it can attract the readers. So then I understood what is the existing phases of TiO2 material. Then I thought of what I can make this material already there. I should tune it so that I can extract something from this. So I can think of the main two important phases of TiO2, which we call as anatase and rutile. Then I understood there are no forms of these anatase and rutile either in the, I have showed in the slide, core shell structures or yolk shell structures or Janus structures. So what is the intention of making these structures is we can modulate the electron hole pairs, which is very important in improving the PEC efficiency. So I have started synthesizing these things and understood the energy landscape with some computational calculations. So after all, what I got is, if I could make the material what we call isometal heterostructures, and I do synthesize it in my lab, and I end up with some important structures with core shell and yolk shell, which have been confirmed with high resolution transmission electron microscopy images. And then with that, I have ended up with whatever the computations has told and whatever the experiments have been revealed, both are matching. And this work gives me a lot of confidence in understanding in the terms of photoelectrochemical water splitting efficiencies. Because if you look at these three forms with the three structures which I have prepared, either core shell, with the energy, with the band energy states, the electron hole pairs have been nullified or quenched. Uh, the same case with the Yolk shell also, anatase and rutile band energetics will not favor, except the Jones structure where the anatase rutile can be facilitatedly used by the species and used for the modulation of electrons. And with that, this work has been, and apart the same work, I understood the phase transformation from anatase to rutile, whether it is surface driven or bulk driven. Some of the computations I have done, and then end up with the structures inside. The experimental confirmation also have given it is bulk driven, but not surface driven. So this work has been published in Physical Chemistry and Chemical Physics recently in 2020, uh, 2020 March. So, but this took a lot of time in understanding the structures, the computations. This is what the experience. So, what I understood is I have not designed any novel material. What I designed is the existing material. I have improvised the functionalities, or I have improvised the characteristics so that we can do lot of wonders. This is what the definition of two. The second definition of a novel material. You improve the functionalities. You improve the maybe the surface characteristics. That will give you the novelty to the existing global material world. And then in the second part of my PhD, I have introduced the concept of click chemistry, where I studied the covalent bond interactions. The what we is covalent bond interactions is usually when we have any catalyst or any particles or nano emulsions, when we want to adhere onto any electrode, we need rely on the physical interactions only or the van der Waals interactions only. But what I have developed is a click chemistry concept which permanently attaches to the existing support by means of chemical bonds. So I have introduced the chemical bonds, covalent bonds to attach any surface to the any particle. This is what the click chemistry. So the concept of this click chemistry lies in understanding the what we call the alkyne moiety and then acyl functionality. So on any surface, if you create acyl group and then some alkane group, in presence of copper catalyst, they form some triozo link, which is permanently sticked with the chemical bonds. So with this approach, I have started some of my PhD work in fabricating some of the surfaces. Like I have done the gold and then some titanium dioxide metal oxides, and then I have what we call find out the efficiencies also. Maybe what that efficiencies, I have designed one more reactor, because ultimately I need a photoreactor to carry out these all the what we photoelectrochemical water splitting reactions. So I designed a reactor. So purposefully the reactor design again, when I design a reactor, it also consisting of the electrodes also, because I need to fit the electrodes inside the reactor, which can harness the maybe the artificial light, which I can keep in terms of light flux inside the reactor. But I need to like overcome some of the things like the bubble nucleation or growth detachments, or sometimes the geometry of the reactor. So with that, I spent a lot of time in designing a reactor with the existing materials. So and I ended up with a very good reactor using materials like PVDF, and then what some quartz type materials, and then titanium as a one of the electrode cathode, and then I used some Nafion membrane, which is ionically conducting. So ended up with a reactor. I can show you the end part of my reactor. Yeah, this is the reactor which I have fabricated at different length scales. And then I have I have used different electrodes materials. This is what my reactors. Um, this is what the design I have done at IIT Kanpur, and this is what the scale up. See, I have started with only 0.5 centimeter square area of the electrode, and then I have what we call scaled up to 25 centimeter square area, and perhaps With this idea, actually, I got a patent, and recently it has been awarded. Perhaps I have filed in the year 2015. I have been awarded in the year recently. I got this grant of the patent, but this took a lot of time in scaling up the reactor because I faced a lot of things. The material is old, but only thing is I need to fabricate with the existing technologies without any deterioration of the material. It should sustain for longer times. So I have published some 2 or 3 articles, maybe in quite a part of my PhD career, like using the click chemistry part. I have fabricated the silicon gold AO2 heterostructures, and then I have prepared some what I call the surface disordered or hydrogenated AO2. We can call it the black AO2, where the surface disorderness improve the mid-gap energy states or oxygen vacancies, which is published in again in physical chemistry, chemical physics in the year 2016. So now with that, this is what the patent I have awarded or granted with the work which I have spent in Kanpur. So maybe I can discuss some part of my 2D materials, which will focus on batteries and supercapacitors. So the intention of the two-dimensional materials, perhaps very important in the context of batteries, which we are looking at, as I told you, as I discussed in the previous slides. Batteries meeting the complete energy demands. Of course, maybe lithium-ion batteries has several disadvantages, but beyond lithium-ion batteries, we've been looking at different materials. That is what the novelty comes. Maybe if you, as I told you, there are two aspects or two parts. You just design a new material, entirely new, from the periodic table of elements, or you take the same old material which is already there in the market or in the prehistory, and then try to harness improvements in that material. This is what the technology is requiring. So I've been discussing some of these two-dimensional materials in batteries or supercapacitor applications. Now, maybe if you go to pre-back histories, where we've been like Stone Age or Bronze Age, or maybe at the later part, we've been in the microscopic age where nanotechnology has emerged a lot in developing new innovations in the market. So the matter of, maybe for example, if I take a oleic acid, where we talk about the hydrophobic or the hydrophilic groups, which repels or which attracts, and then where we will see the what we call the matter of size, because at the nano scale there are a lot of inputs, maybe the electrical properties or chemical properties or mechanical properties. The properties will change from the bulk to the nanoscale. Here I have showed you some zero dimensional. Zero dimensional means all the dimensions are nano only. But if it comes to 1D materials, means dimensions are nano and one dimension is bulk. So whereas 2D, only one dimension is nano, and that is the one dimension is nano means the dimension is like thin films. We can call as thin films, or three-dimensional. Entire thing is microscopic only or macroscopic only. That means all the bulk only, but not nano. So there are a lot of examples in all these classifications, and here we will see only the two-dimensional materials because they will give the discoveries of 2D materials has given a lot of advantages or lot of improvements in the existing materials market. For example, you look at the thing called graphene. So we've been looking every day. There are a lot of articles, journal articles on the graphene. So 2D materials are thinnest nanomaterials, perhaps at the scale of nano or at the scale of micro. So, for example, if you could have a sheet-like structure, and we maybe the link between the two layers been van der Waals, but that will give a lot of properties, maybe at the electronic properties because it's a semi-metal or semiconducting, or the other forms of carbon allotropes. Fine. So we will end up with so many lot of innovations in just manipulating the matter at the nano level. if you could arrange the atoms or the molecules at the nanolevel, you can do some miracles. This is what the innovation of these amexins. Let me show you in the coming slides. I will show you the amexins. So the first part is the graphene. Graphene has it's like a semi-metal, very high surface area. Perhaps it is almost 2 times than the carbon nanotubes are, and extremely what we call the electrons have high speeds. Fine. So maybe it has very high mechanical properties. In fact, it is, see, look at 300 times harder than the steel. So tensile strength 130 gigapascals tensile strength, and it is stretchable up to almost 20 times of its length. Because of these peculiar specific material characteristics, graphene has been used tremendously in so many applications. Maybe I can show you some of the slides because of the look at the other properties. The thermal, electrical, optical, all are I can say the assets for a graphene, where the flexible graphene transistors are available in the market, solar cells, conducting materials, or we can perhaps we can use it in the mobiles, reactive carbons. So all are of the graphene only. And let's say the more innovative novel materials are amexins. These amexins are introduced in the year 2001 by Yuri and Michael groups. And what we mean by these amexins, it's a new family of graphene-like 2D structures where we use carbides, nitrides, or composites of carbonitrides. So what exactly you mean by this max is M, and then A, and then X, where M is a transition metal, A is a group element, and X is whatever the carbon or carbide or nitride. So if you look at the symbols in this periodic table, you look at the X. This is the carbon and nitrogen in the black symbol, and look at the blue color, where we call as the transition metals, maybe titanium, vanadium, zirconium, hafnium, niobium, so or tungsten or molybdenum. So there are a lot of combinations of these M, A, and X will lead to end up with amexins. So how do we form amexins? I will show you in the next slides. Maybe you can look at this amexins. So it's like selective layer etching. So if you look at this MAX, so slowly we can use HF etching, hydrofluoric acid etching, to remove the A, and then we form amexins. So why this name amexins has come is because it has similar properties like graphene. We use the word ions in this max. So amexins we can call as. So this is what the selective layer etching. So there are important combinations of M with important combinations of A and important combinations of X. We can do some permutations and combinations to get lot of compounds with these amexins. And in fact, this literature studies confirm tremendous improvement in the efficiencies, either in terms of batteries or supercapacitors in storing the energy. These amexins playing a prominent role now. Maybe I can show you some of the slides. You look at here, magazines. It's like transparent sheets with the combinations in the periodic table. So perhaps I can show you. Yeah, it is typically made of highly conducting. So they definitely you go for this carbide and nitride combination, and then try to remove the what we call the H. I can say the H, the A element. So there may be like you can produce in 3 different flavors, maybe 21 structures I just showed here, 21 or 43 or 32 structures. So the synthesis part. So we definitely go for HF etching or HCl etching. When predominantly we go for HF etching only, and perhaps these are highly soluble in water, ethanol, dimethyl sulfoxide, DMSO, acetone or acetonitrile. And I can show you the applications. Yeah, you can look at these applications. High volumetric capacitance. You look at the value 900 faradays per centimeter cube, and then maybe almost 100% coulombic efficiency if you go by this titanium carbide. How they have chosen this titanium is M, and then this X is carbide. So this is what amexenes, where A is etched out. So this is what the synthesis of amexenes leading to high volumetric capacitance and then coulombic efficiencies. And then in fact I can accommodate in these materials the percolation of H plus or lithium plus or sodium ions or magnesium ions. So this is what this article published in Nature. And sometimes not only the battery or supercapacitor applications, we can look at some tantalum carbide composites, because tantalum again comes under the M category, and then X is the carbide nitride. These have some medical applications that's called breast cancer theranostics, and this is what showing high photothermal conversion capabilities, maybe in what we call drug delivery applications or tumor detection, and some highly biocompatible. This is also article published in 2018, and entirely it's a novel material. And what MAX is a combination. They've been trying to detect some cancer or tumor sites, maybe in the light contrasting or MRI agent. They have been detected in this article. And then other class of materials is TMDCs, which again comes under a utilization of sulfides, tellurides, and then selenoids. So this is formulated as two-dimensional XTX sheets, and then every sheet is tri-layered with titanium atoms sandwiched between two chalcogenide layers. So this also has tunable properties and has a lot of applications. And I can show you perhaps all are for the either batteries or supercapacitors. I can show you here the two different octahedral or tetragonal plastic structures which can lead to applications in supercapacitors, which is published in Springer in the perhaps in the year 2019. Yes. Now, what we call tungsten sulfide layers. This is also one form of a novel material where exploited the tungsten with sulfide groups, TMDS, what we call as, and then this also used. This is a high performance core shell nanowire supercapacitor, which is made up of tungsten sulfide layers, and which is published very recently, 2016, in ACS Nano. So the synthesis is a general synthesis. Only thing is we can manipulate, we can what we call we can optimize, and then we can extrapolate to get the required structures. And again, the one more TMDS in case of now the batteries. What exactly these dichalcogenides? They may even have some weak interlayer coupling, disordered octahedral structure with triclinic system, but they've been long lost in batteries and supercapacitors. So this is what have lot of papers. Here I have clubbed 3 papers which are all talks about these materials, TMDs materials. So all these materials, you need to understand in a more material perspective, and then it takes there will be a lot of challenges even synthesizing, even for the case of graphene. Even if you control the parameters during the experiment, it always there is a more probability to form graphite rather than graphene, because these graphene, to make the sheet-like structure, we need to control the parameter like pH, and then what we call the temperature or the stirring rates. It's always a challenging during the synthesis to get these materials in hand to have some fruitful results at the end of the day. Some part of materials in the same batteries or supercapacitors, the MOFs, we can call as metal organic frameworks. So what these metal organic frameworks? It's a coordination polymer, alternately with coordination network in an open frame network. Fine, and majorly we use copper and then zinc, manganese, cobalt, copper. So different structures we can have, and it has several structural features. Like it has large voids, so that the gas diffusion can take place very easily. So we can study these metal organic frameworks for storage of hydrogen, because as I said in the challenges slide, storage of hydrogen is earlier is a very highly challenging, because storing, because hydrogen itself maybe in the gaseous form or liquid form, it is difficult to store. So metal hydrates, metal organic frameworks, it can be used in capturing the hydrogen. So there are a lot of I can say the properties of these MOFs, which and even these MOFs, maybe we can go for the electrical insulating applications, and sometimes these MOFs highly suitable for desalination or wastewater treatment, some membrane applications. Like more often we go for peroperation applications of these MOFs. And the important thing is, like, we can modify the structure surface characteristics. Like for example, it is easier to change the or it is easier to terminate the surfaces, maybe with the hydrophilic groups or hydrophobic groups, with the desired application which we want. And more often these MOFs will be used and securely for hydrogen and CO2 capture. Even as I told you in the previous slide, carbon dioxide, uh, which we want to capture and then convert into usable fuels, wherein we can decrease the carbon footprints. So MOFs play a very important role in capturing the either CO2 or hydrogen. And these are the uptakes, volumetric uptake of CO2 in one of the studies. This is what references. So these are all what I can call open metal sites with some basic sites with different pore size and pore size distributions, which can allow the gas to diffuse and capture inside the materials. And for some of energy applications or energy storage applications of these MOFs, these two articles, which are again recently published in many good journals, and again it plays an important role in understanding these MOFs. Either I'm going with the MOFs with a 2D layer or 3D layers. So it's important to manipulate or it's important to play around the temperatures or some other critical parameters, which can end up with the structures which will again characterize, conform, and then utilize for the application which we desire. And then other part of the materials comes under this batteries and supercapacitors are covalent organic frameworks. We can call as COFs. So covalent organic frameworks, again a class of crystalline porous organic polymers connected by organic building units through covalent bonds. So this is first reported by Coate and Yagi, and perhaps they are also 2D materials, and sometimes we can go with the 3D also. We can synthesize the 3D COFs also. And again, what our place is the internal structure manipulations. What is pipette stacking, and then whether we have hydrogen bonding or van der Waals interactions, and then what is a polar and what is a non-polar, and what is this polar non-polar with the support which we take, and all these making to utilize the end application of this covalent organic frameworks. And this is the structural characteristics of COFs. I can tell you these several what we call the attributes of these COFs. Maybe I can say I have left-ended. I have put it up. Low density, high surface area, very highly tunable pore structures, and tailored functionality, and then covalent combination. I can play around a lot of things with these COFs. In fact, these are like lot of call articles are published using these COFs. Even in the medical aspect, also these COFs have been highly used, even for the drug delivery or drug targeting. And what these COFs in energy storage. Perhaps I have given you the two important articles of these COFs. In one of them is in supercapacitor, and other is in the metal ion battery. And this metal ion battery, and perhaps this metal ion battery comes under either sodium ion or lithium ion battery. And what these COFs, 2D crystalline porous extended organic materials that have shown here, have given these promising results. If you look at this volumetric capacitance or the cycles, the material durability, how many cycles it withstands, or in the terms of Coulombic efficiencies, these materials have proven a benchmark materials. So that is why the innovation, and earlier in the first slides I talk about the two important parameters, the scarcity and the innovation. So the technological innovation and the improvements made remarkable. That's what maybe the bet of Simon and Paul um, made in 1980s itself. So those two scientists really, the paper in that science given a lot of people in encouraging and drives towards the research, how we can synthesize or how we can fabricate the materials. And another graphene or boron nitride materials for membrane applications in the fuel cells. Perhaps we know the importance of fuel cells. It may be methanol fuel cell, fine, proton exchange membrane fuel cells. And what here the fuel cells is the internal parts. Every internal part plays an important role. You know, sometimes we will look at the membrane, sometimes we look at the polar of the other end, carbon electrodes of the support layers. So all in all, in order to improve the fuel cell characteristics, we need to rely on some material perspective only. So here, this article has 2D material graphene sheets. One of the applications they have implemented at Rice University and University of Manchester, and they observed almost very good efficiencies reported. And last part of the materials which I am which in this talk consists of this phosphorin, so which is a single layer of black phosphorus. Again, it's a layered stable allotrope of phosphorus. It's again a direct bandgap semiconductor material with a honeycomb structure. Maybe I can, at this point of view time, I can tell you about this honeycomb or perovskite type of materials for the solar cells. So again, I can say the in earlier days only silicon is the existing material for solar cells. Silicon, or I can say gallium or indium materials. But this innovation or what we call technological edge of perovskite materials made a lot of changes in the solar cells. Also now very thin solar cells are coming into the market at lower cost and uh, in the global material scenario. So this material phosphorin, it's a direct band gap semiconductor material, almost highly charging material. It has a good charge mobility. Maybe I can see here, I have marked here 1000 centimeters volt per second. And that's why, because of this high charge mobility, it is used in more optoelectronic devices and transistors. Um, and I can summarize my talk um, with a few points which I have been discussed in the entire of my slides. Though I have not like in depth, I have gone through the material sector, but I have given the glimpse of the materials. So the talk summarizes the discovery, development, and deployment of the novel materials, which actually plays a significant role in the human civilization development. Maybe these materials are like connected to the technology or economic activity, but more focus is on changes, technological developments, or improvements. So on par with the existing applications of the users. So the improved efficiency and functionality of the materials can bring tangible environmental benefits and materials innovation, which can reduce the cost and fetch the search for the alternatives. So all in all, the take home message from my talk is, when we are looking at some application, better rather to go at the broader end of the innovation of preparing from the scratch. Take a material as it is available and understand at the microscopic level. Think of the maybe if it's for example, if it's semiconductor, understand the band gap energetics, and why we can call maybe in a semiconductor physics we can call as a band bending. Why the band bending is upward or downward, and can I make the band bending a little bit up by providing some bias. And if you think like that, you can really get through or really prepare a novel material for the existing applications. So this is what the conclusions, and I could acknowledge a few of my students, my supervisors, Dr. Sri Sivkumar, professor of chemical engineering at IIT Kanpur, and Dr. Raj Ganesh Pala. And I can acknowledge two of my gurus, Professor S.V. Satyanarayana and Dr. Dinesh Shankar Reddy. And these are my student collaborators, or I can say the student researchers who are working with me in all part of my research outcomes. And perhaps I have won some of the awards during my PhD study. This is Gandhian Young Technological Innovation Award given at IIM Ahmedabad. And then this is one more award at Primary 83 Innovation. This also I got a cash prize for my research work at IIT Kanpur. And perhaps I have showed you one of the patent granted recently. And this is one of the like the paper which I have presented in ChemCon 2013, got the first prize. And these are the recent published articles in good reputed journals related to the materials. So which I have synthesized, perhaps here it maybe I have synthesized the zinc oxide by manipulating the material properties, or I have showed you the recent published KAO2 material journal, which is published in Physical Chemistry, Chemical Physics. And I have synthesized some more paper. I have published some more works on zinc oxide, and then some membranes with my collaborators, Satyanarayana sir, and then one of my student, which is recently published in 2021 Korean Journal of Chemical Engineering. And this is one journal where I talk about this graphene, prepared the graphene oxide and then utilize it for some applications. And then some of few articles where I prepared some heterostructures with titanium dioxide or iron oxide materials, recently published articles. Fine. So I thank you for all like for patient listening for all the time, maybe in the afternoon session. And I end up with one quotation because as I discussed about main important point of water, where I'm breaking into hydrogen and oxygen. So, which perhaps water will become a coal in near future. So, no doubt about it. This was earlierly, this was way back given by John Verney in one of its article in 1874. And this is really true in the sense we are looking at the renewable sources wherein our fossil fuels are depleting day to day and creating a lot of carbon emissions and leading to a climatic change or global warming. So thank you one and all, for maybe the organizers for giving me this opportunity to share my knowledge and share my research experiences during my PhD work. Thank you.
Thank you.
I'm ready to answer if you have any queries.
If anyone was interested to question, you can put the questions to sir, or you can write in chat box so that sir will answer to those questions. Any participant? We will wait for a few seconds, sir.
సార్ ఇట్స్ నాట్ ఎ క్వశ్చన్.
Yeah, yeah.
దిలీప్ గారు నమస్తే. నా
Yeah.
పేరు డాక్టర్ పివి వినయ్. నేను గాయత్రి కాలేజ్లో పనిచేసేవాడిని మీతో.
Okay, okay,
ఇఫ్ యూ
okay,
రిమెంబర్ మీ.
okay.
ఇట్స్ అ లాంగ్ టైమ్ దట్ ఐ హావ్ సీన్ యూ. I
Oh,
used to be in mechanical engineering.
okay, okay, okay. Sir, I couldn't remember you. Perhaps.
I'll I'll just switch my camera on. Just a minute.
Venkata Vinay.
అక్కడ
సార్ ఏ
నేను
డిపార్ట్మెంట్? ఫిజిక్సా?
నేను మెకానికల్ వాడిని.
ఓకే.
కంప్యూటర్స్ ల్యాబ్ దీనిలో ఉండేవాడిని, డేటా సెంటర్లో.
ఓ ఓకే 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 గుర్తుకొచ్చారు. ఎలా ఉన్నారు?
ఓ ఫైన్, బ్యూటిఫుల్. ఇట్స్ బీన్ లాంగ్ సిన్స్ ఐ హావ్ సీన్ యూ.
Really, thank you so much for remembering me. Even in
నో
fact,
నో
it's
నో
గుర్తుకొచ్చారు సార్. ఎలా ఉన్నారు?
యా, it's been long. Last time I wanted to talk about something, but I couldn't get a contact with you.
ఓకే ఓకే
But
ఓకే.
it's nice hearing you talk. It's very good. The new materials that you have synthesized, it's nice. Some areas this time it is a very good. Completely, I should say, all the sessions are very nice, especially yours too, because the synthesis that you have been doing, majority of the people have not come into this area, because composites, whenever we talk some mechanical or metal composites, wherein we just mix up some material into the aluminum or any other material. But synthesizing nano level composites and then mixing them is what has been growing, and it is
Yeah,
very nice to see that it is on the easier side too, rather than we going to someplace else, go for a huge process called a ball mill, which is going to take a lot of time, again going for analysis, so on and so forth. But the chemical route looks to be very nice, looks to be more promising this time.
yeah,
Hopefully this will give more impetus into research in these areas, especially to all the researchers who have been listening or all the students who are seeing. It would help them,
yeah,
because this is nice area too, fast growing, and it has more societal importance also,
yeah,
because this is where the country is in need of, especially. And as you rightly said, that energy is the next big thing.
yeah,
Everybody is looking at hydrogen or electricity now, but again electricity storage is another main problem. Again, fuel cells, the amount of research that has gone in has been like since time immemorial. Fuel cells have been researched since what, 2003 2004, still the research is going on in fuel cells. Storage of hydrogen is the new in thing now. It should be, again, I hope storage of hydrogen has also reached a saturation point. Now transport of hydrogen should be the next big thing. At compressed levels, storing as well as transporting hydrogen, uh, again, is the area that is being worked now, because all IITs are working on hydrogen fuel cells. Majority of the places are working on hydrogen storage. Hope hope this brings more energy independence to India. Hope we get energy independence by 2025, because the government, the push that the government is giving for electric vehicles and all, most probably research is also going to increase those many folds. That
yeah.
is what is happening. Thank you so much, sir. Thank you, Dilip
Sir,
Garu. Thank you for
thank you.
everything.
Thank you
Thank you,
very much.
Damodar Reddy Garu, for giving
Thank
the
you.
opportunity to talk to. Thank you very much. Thank you.
Thanks, sir.
Thank you very much, sir.
Thank you. Thank you.
Thank you.
So, anyone would like to ask any questions? Any participant? So you can write an email to sir, and the sir email address will
Yeah,
be given.
I can put my email address and then phone number. If anyone want to have an interaction, they can directly post. This is my email ID, and keeping my mobile. I'm sorry, I'm not using the smartphone. You can just text message if you have anything to discuss or talk. So thank you very much, Damodar, for giving me an opportunity to interact and share my experiences, what I've gained or research. Thank you. Thank you very much.
Thank you to one and all. I need to thank to Dilip Kumar sir once again for having a nice, wonderful, and beautiful lecture. Thank you, sir.
Thank you. Thank you very much, sir.
Thank you.
Thank you. Thank you all.
So